So what we're going to talk about during this webinar is basic GPR theory and how it applies to locating utilities, the LMX-100, 150 and 200 utility radars, how GPS can be integrated with GPR data, and the ECHO project software. So we'll start with basic GPR theory. So GPR means ground penetrating radar. When we talk about the ground, this can be anything. It could be soil, concrete, rock, wood, anything non-metallic. So what we do is we emit an electromagnetic pulse, and that will go in the ground and reflect off something in the ground which is different from the homogeneous ground. And we record these echoes, these traces, and we build a cross-sectional image from the echoes. We commonly refer to these echoes as hyperbolas. So you may hear me talking about hyperbolas. These are just traces created by the GPR. The simple way to think about it is it works like a fish finder. So the water is all the same. So if we send a signal down through the water, that signal is going to bounce off the bottom. Now, if there's something in the water that's not water, in this case a fish, we will also get a reflection from that. So we'll see something in the water column which is not water, which is something different, which is what radar sees. We're talking about homogeneous ground, the ground is all the same, and then suddenly it's not, there's a change. Now, the targets are located at the apex of these hyperbolas. So we've got three hyperbolas here, and the target is located at the top of them. Now, the reflection itself is made of 3 or 4 bands of energy, but it's only one object. We can't interpret the individual bands. Together, they're all one reflection. And the depth of the object is at the top of the highest band. So how do we gather this data? And how do we form the hyperbola? So to start with, we've got 2 axes. We have the positional axis, and this is determined by a digital odometer, which is on the back right-hand wheel of the GPR. Then we have the depth axis, and this is actually a measure of time. How long it takes our signal, when it is emitted from the radar, to travel down and bounce back. So when we talk about time, depth, we're actually talking about time. And we're measuring this time in nanoseconds. So as we push the GPR forward, we go over objects and we form hyperbolas. So why that shape? Well, the energy from the radar actually comes out in a cone. And as we move forward, at this point, we can actually start to see the object. And because it's on a slope, if we bring that slope across to directly underneath the radar, it makes a reflection deeper than it actually is. Then as we move forward, the object seems to get shallower until we get right above it to the apex, and that's the actual height of the object, the depth of the object. And then as we go past, we're still picking up the object as we go past it. So that's how we form the hyperbola. Now, it's important that we try to cross the targets at right angles. You can see here, if we cross here at 90 degrees, we get a nice sharp hyperbola. If you cross at an oblique angle, you'll start getting wider hyperbolas. Now, if we go directly along the object, what we'll get is an approximate flat line. So here we have a storm drain, and the intake is here at the right, and it falls away to the left. So there's our storm drain direction of fall. If we bisect it at point 1, you can see here we have hyperbola at about 1.2 meters. 0.2. And we're seeing now we're down at 1.5 meters. Bisect at 0.3. 1.8 meters. And if we travel straight along it, you can see there the top of the pipe. If you look very closely, you can also see the bottom of the pipe. So there we see our 3 cross sections and traveling along the pipe. So what's tough about GPR? Well, the ground's complicated. GPR images themselves contain a lot of information. Some things will not reflect. Some soils absorb all of the energy very quickly. And GPR detects everything, not just the stuff you're looking for. You must understand the context. We get GPR with GPR data sent to us and people ask us about it. And the first question you say, well, we need some context. You know, what were you looking for? Where were you? So you need to know the context to understand what you're looking at. So when we talk about solutions for location, there are a wide range of solutions, and no single technology will locate all utilities. EM devices are the most common. Some of you may use a precision locator, some may use Cat and Jenny, but they're both EM. But GPR use is increasing. It plays a vital role. It has limitations, and they must be understood for proper use, but it has a vital role in especially the area of utility avoidance and location. So EM methods, they make sense when you're looking for metallic targets or something with a tracer wire. You could directly connect to it or induce a signal into service, and you're looking for single utilities. Where EM methods are less effective, looking for non-metallic utilities. When we need visual records, if you locate in or through reinforced concrete, and if you were detecting multiple utilities or looking for multiple utilities in an area. So advantages of GPR. You may find unknown targets that are not in any drawings. It has the potential to see very deep. You can cover large areas very quickly or reasonably quickly. You have a visual record, and we can provide accurate depths. So what sort of terrains are suitable for GPR? Well, soil, sand, grass, asphalt, concrete, block paving, and snow and ice. These are all suitable terrains. Challenging situations include anything that's got salt water in it, heavily fertilized soils, and clay-rich soils. And then anywhere we have problems with deployment, so a lot of rocks, loose rocks, and tree roots. Here we'd have challenges with deployment with GPR. So the LMX range consists of the LMX-100, the LMX-150 finder, and the LMX-200. So it's a one-person operation. We have a high visibility touch screen in all of these units. They're very weatherproof, lightweight. We have built-in GPS. There are options for external GPS with the LMX-150 and LMX-200. We have built-in Wi-Fi for exporting mini reports. And the menu system is very, very easy to use. And our data download is via USB. We also have a series of integrated self-tests, so you can fully check your radar before you deploy it. So when we're talking about GPR, a lot of time we talk about frequency. Well, so which frequency is best? Well, we have the frequencies go from very low frequency to very high frequency. So there's 3 things to think about: frequency, resolution, depth of penetration. So as the frequency gets lower, the depth of penetration increases and the resolution decreases. So we've got to find just where we want to position ourselves for whatever job we're doing. So glaciology, we would be talking about very, very low frequency biostatic antennas. Geology, again, low frequency biostatic antennas, a bit smaller. And then we get our 100 meg antennas, which we can have as biostatic or with our noggin system, we can put them on a cart. Geotechnical, sinkholes. Then we get into the utility locating range, 200, 250, and 500. 500 we also use for archaeology, forensics as well. And then when we're at 1000 meg, we're talking about concrete and roads. So the LMX-100 and 200, they fit just about here. So we've got a 250 meg ultra wide band antenna. And the LMX-150 has a 500 meg ultra wide band antenna. So 250 meg ultra wide band antenna, that means the effective frequency range is between 125 and 375 meg, centered on 250. And that's the most effective antenna for broad range of utilities. And the maximum depth is 8 meters. The LMX-150 has a 500 meg ultra wideband antenna, and this has an effective range of 250 meg to 750 meg. So it has a wider frequency range due to its higher frequency. So with this, we get great resolution. So it's the most effective antenna in our range for shallow utilities. When I say shallow, the first couple of meters. And that has a maximum depth of 3 meters. So we'll start looking at the LMX-100. There's a lot of commonality in here. And when I move on to the other radars, I won't be covering the common elements. So rapid deployment and setup. We have a sunlight visible touch screen. It's easy to operate. There's very, very few parameters to set. And again, as we said, it's Wi-Fi capable. And with this, we only have internal GPS. And from there, we can, from this unit, the only thing we can save is screen images. So if we switch on, we have soft keys on the touch screen, and we have hard keys below. So if it's raining, our screen is not that affected. But you can, if you don't want to use the hard keys, soft keys, you can just use the hard keys below. USB port for data download, and in our tools menu, which is just here, we have preferences and system test. So we're going to click on preferences, and here we've got it in English, United Kingdom, metric units, date and time, and here we can we've got volume, brightness, our Wi-Fi network, and we can also, if we pull that down, we can set our initial contrast brightness. And then we have our system test. So system information to start with. Now, if you phone up technical support, there's some information on there we may ask for, the serial unit of the DVL and the antenna serial number. But on here, we can see our battery level, and we can see, look, all the other information is mainly the sort of stuff we're going to ask for in tech support. GPS, of course, with the LMX-100, we only have internal GPS. And we can hit the GPS test button, and we'll just see the NEMA strings floating by. We have an audio test, which just checks that the speaker's working correctly. The GPR sensor test. We just rock the GPR up on its back wheel, press the start button, and that does a test on the GPR sensor. Very important test just to make your sensors work, sure your sensors working correctly before you use it. The odometer. With the odometer, we can either do an odometer test, which we do over 5 meters. We will get a pass or fail over that distance. If it fails, or if you're changing the surface you're working on, you need to do an odometer calibration. And you do this over 5, 10, or 15 meters, or a custom length. I always recommend do your odometer calibration over the longest distance you can. And you'll get a new value, and it's either going to be in range or out of range. So that one's good, so we accept it. Keypad. Here we have to make all of the keys on the screen disappear by pushing the hard keys. And that makes sure that every hard key is working. And then we have a touch screen test, which is like every other touch screen test you've ever seen. So we hit the start button. We have down here, we have our screenshots and our flags. So if you want to leave a flag at the start, you can leave a flag. Now the flags are just numbered sequentially, and these are for above ground observations normally. So if we drop a flag in a certain place, we can make a note in our field book of what that flag represents. And as we push along, the GPR signal, the GPR swathe starts to form, and it forms from right to left. So we're going to pop into line view settings, and we could do, if we pull the radar back, so we're here, if we pull it back, a little radar appears at the top of the screen and a line appears on it with a cross on. We can move this cross up and down to measure the depth of our hyperbolas, and we can do a hyperbola calibration by bringing up this virtual hyperbola, which I'll talk about more later on. Soil cal, and this is where we do our calibration. So different materials have different properties, so the GPR signal travels through them at different speeds. So you can see here, air is 300, and that's million meters per second. And then we go all the way down to water. So depth of the object, or calculating the depth, is determined on the speed. So we need to know the speed, or the speed at which a signal travels through the host material in order to calculate the depth to the object. If we press the screen, just touch it, we will bring up a spot position and spot depth. And we can drop the flag on the screen by pressing the start button. You can see here we've picked up 2 hyperbolas. So what I'm going to do is I'm going to pause, move the radar along the line of the utilities, and I've gathered those 2 lines again. And I can just draw an arrow on the screen. And draw an arrow on the screen this side to identify the same targets. And now I can take a screenshot. Now if I exit and go into my screenshot gallery, we can see here the screenshots that I've taken. And we download those screenshots via the USB. So we plug in the USB, And we get a little question box. Would you like to download it? Yes. And we're downloaded. If you go to the top of the LMX screen and pull down, here you will get some quick information about the battery status, and here you can change your volume and brightness. So the LMX-150 and the LMX-200. As I said, there's a lot of commonality, but there are more things we can do with these. These are for the professional utility locator and engineers. All the features of the LMX-100, but we can also process onboard grids, and we have the option of external GPS. And with these units, we can download and post-process our data using our Echo project software. So we're going to switch on. Go to tools. So we have preferences, system test, and now we have one called file management. So in here we have we can have 9 projects, and each project can have 10 grids, 99 lines, and 1,000 screenshots. And the longest line you collect is 1 kilometer. If your project is in red, it's in use. If it's green, it's free. So we're going to go into line scan and start. So now what we're going to do is we're going to look at what all these things on the screen mean. Well, we have the positional axes along the top, the depth axes along the side, and our GPS quality in the bottom left-hand corner. So GPS quality, we can see quite quickly whether we have how many fixed satellites we have, between 4 and 10 plus. Down the bottom, we have this blue line, and this is our dynamic quality control, or DynaQ. And this is to do with something called stacking. So DynaQ stacks automatically when using an odometer. The amount of stacks vary with the speed at which you push. So slower speed, more stacks, and faster speed, less stacks. And there's an optimum number of stacks where it won't stack anymore. I believe that's 8 stacks for these units. So what is stacking? It's an averaging. So it averages out to get rid of the noise in the signal to noise ratio. So if you look at 1 stack, we'll have our signals with a bit of noise there in red. 2 stacks, we do some averaging and the noise is a bit less. 4 stacks, we do more averaging and the noise is a bit less. And 8 stacks, which is the optimum amount we're set to. And you can see there, with a bit more averaging, we get rid of a bit more noise. We do systems that stack thousands of times, but not within the utility range. Some of this, some of the stacking can take quite a long time. So we're talking about workflow and what is optimum within the workflow, because the more stacks, the slower you're going. Zoom. Well, there's 2 things on zoom: depth of penetration and position. So with the LMX-200, we can go between 2 meters and 8 meters. And with the LMX-150, we can go between 0.5 meter and 3 meters. And the positional scale, how much of the line we see on the screen goes between 10 and 30 meters. We have a choice of color palettes. We can see here, I much prefer grayscale, but if you want to use something else, well, the color palettes are there. And we have a filter selection. Now, filters remove long flatline objects. So the first thing I'm going to remove is what we call the first return, the ground return at the top. So we see here the filter's off. And then if we apply a low filter, that just removes long flatline objects. And as our filters increase, it starts to remove smaller and smaller flat objects. So low filter levels apply a long filter width, only long flying features are removed. And high filter levels apply a short filter width. So that removes long and short flat objects. Gain level, gain goes between 1 and 9. And we can see here gain level 2 and gain level 8 in the same area. So we just pick the right gain level for the right ground conditions. Dynity, now Dynity, because we have ultra wideband antennas, and what we can do with Dynity is look at the low end of the frequency scale within the frequency band of the radar, the middle and the top, or all at once. So you can see here, small, medium, large, and all. So we're going to try and highlight the smaller objects, medium-sized objects, large objects, or just have an amalgam of them all. Dynity can be very useful for highlighting objects because we've got such a wide frequency band. Just looking at the different parts of it can be useful sometimes. Calibration. This is, as I mentioned earlier, this is soil calibration, and this is calibrating the velocity of the signal through the coarse ground. So when we press soil cal, we have a virtual hyperbola. Now this is pre-programmed with an algorithm, so we actually move that wider and narrower, and that width relates to a velocity. So we just match the shape of the tails on the hyperbola using the virtual hyperbola that appears on the screen. And when they're matched, we press the apply button, and that applies the correct velocity for that ground. Field interpretations. With field interpretations, we can drop dots, different colored dots, on objects on our screen. And we can look at them in map view when we bring up map view. The grid scan, we have preset grids, 5 by 5, 10 by 5, 10 by 10, 15 by 15, and you get walked through how to collect the grid. Now, grids are used for getting grid slices in the field. With our grids, we don't have to collect all the lines, and we can also collect around an object. So if we only want to collect so many lines, we can skip the other lines if we have a different shape. And then when we've collected all our lines, we can go into slice view. And when we go into slice view, we can slice away the ground and look at the objects in different layers. And you're literally removing the ground layers one at a time. So you see here, I've set up a grid with flags. And then when I've put my slice view through, you can just see there, I'll run through it again. You'll see a couple of pipelines appearing now and running down through the ground. We have a nice feature within Echo Project, our software, called Photo Slicer, where I can overlay the GPR images onto the photo I've taken. And you can see there, we've got the same thing again, but it's overlaid on the photo. And there are actually two pipelines, two pipes there, the 4-inch pipes that run down the back of my garden. We could also output this as a 3D cube. Oop, go back one. And it doesn't want to play. But you can see we've got that with inside a 3D cube. Now, using GPS data, we can use this to augment the GPR data for geotagging. And you can see on the right-hand side picture where there was utilities running through people's gardens, and we've mapped them out. And that was using GPS. So internal or external? Internal, it just provides geotagging, accuracy plus or minus 5 meters or so, pretty much the same as your mobile phone. External, with the Trimble GPS that we supply with the system, this is 1 to 2 meters within the survey itself. It's a whole survey shift, it's not between points, or you can use an RTK antenna to give you sub-centimeter accuracy. And here's map view. So we've got GPS, we can enable map view, and we can see here everything we've collected. And there we've got our grids and our lines and map view. Now with the LMX-200, we have split view. So we have our GPR swathe on the left and our map view on the right. And then we can switch on and off different layers. Now with GPS, it also allows us to do something called a pseudo grid or a free run grid. And we can overlay this onto Google Earth. Now this is a street where I live. And I collected a 1 kilometer line up and down the road. And from that, I processed a grid. And we can see here slicing through the ground, and you can see the laterals growing across the road. And eventually you can see the sewer coming in as well. I'll run that back. There we have the sewer. And a bit shallower, we have the lateral connections across the road. And then this red here is where we've got the road structure itself ending at 500 mil. And we're going into ground after that point. So we can do some quite interesting things with Echo Project with these lines. The software itself and the GPS software, the GPR software, it's called Echo Project. So it starts with something called Echo Project Core, which is pretty much a viewer. We can do a certain amount of things from reports with it, but it's more of a viewer than anything. Then we have a package called Examine, where we can put interpretations onto our line views. Reveal, this is where we also incorporate the grids. 3D Reveal, which includes the 3D software. And then Suite and 3D Suite. The thing that you're adding to them here is the processing module. So lots and lots of different things we can do with the software, generate reports, outputting KMZs, outputting a CSV spreadsheet, AutoCAD, we have photo slicer, 3D previews, and we can also output lines in point cloud. So this would be Echo Project Core, and this would be Echo Project Examine, where we can add our interpretations on there. And this would be Reveal, where we can use Slice View. So outputs, LMX-150 and LMX-200 are able to output a number of formats. LMX-100 can output screenshots. The LMX-150 and 200, well, we can output to Google Earth. We can output photo slices. We can output to Voxler 3D. Working this time. We can generate a summary report to give to the client. We can output an AutoCAD. I prefer to output a CSV file because I prefer my output in layers, but it's up to the individual. Or we can output point cloud. And our project report, so here I'm outputting the water. Got a lot of information. The bits I want, I'm just going to extract. And there I can output this to my CAD drawing. So which model's right for you? Now, if you just want to put a mark on the ground and find utilities prior to excavation and take screenshots, well, LMX-100. That'll do everything you need. But if you want to record the positions and create depth slices, export into Google Earth and generate reports, or perhaps export to a model, you're looking at the LMX-200 and LMX-150. And we can see there the green bits are the differences. So choosing LMX-150 or LMX-200. For the broadest range of utilities, or when the soil conditions are right, LMX-200 is recommended, as the 250 meg antenna has the potential to see deeper. The great potential, the potential depth range of the LMX-200 means it is usually the preferred solution for people undertaking a wide variety of GPR activities. So you can see there the response from an LMX-200, and this is the same response from an LMX-150 on the same utilities. For shallow utilities or better resolutions preferred, LMX-150 is recommended. It also has a smaller footprint, so you get increased resolution in the top You can see down to 3 meters, but we're usually talking about the top 1 or 2. So it's often preferred for shallow services such as pavement work. And we see here the response from an LMX-200 on the left and the LMX-150 on the right. And I think this one is more telling. So LMX-200 on the left, LMX-150 on the right. Now, there are some soil conditions where you don't gain any depth benefits with an LMX-200, and we've seen this where the depth penetration is challenging. We're still seeing as deep with the LMX-150 as LMX-200. So some soil conditions mean that LMX-150 would always be the preferred option, but some soil conditions mean that LMX-200 would be a preferred solution because you want to see the deeper stuff as well. So the water myth is water causes GPR to be ineffective. The water fact is fresh water is one of the best mediums for GPR. So we can see here, we're towing a GPR in a boat, and we can see the bottom of the lake, and we can see into the bottom of the lake, into the silt at the bottom. So it's actually the polar nature of water molecules. That means it dissolves ions, and that makes the water conductive. And that's the thing that absorbs radar signals. So conductive soils absorb GPR signals. If you've got conductive soil and you get water on it, the water absorbs the minerals, and that causes problems with depth penetration. So it's the dissolved minerals which make the ground more conductive, which attenuate the GPR signals, limiting depth of penetration. So it's not the water itself. Sometimes you get if you've got you've got a lot of minerals in the ground which are conductive, they will be absorbed into the water. Now, where people think GPR signals get blocked out by water is a thing called water clutter. And this is if you get the bottom of the antenna, I don't mean like wet surfaces, if you actually run the bottom of the antenna through shallow water. What actually happens is the signal gets trapped between the bottom of the antenna and the road surface, and it bounces around in there. And you get a similar effect as you get with a metal object, shallow metal objects. And we call this water clutter. So this is what people think water does.